March 12, 1943, Piedmont Army Research Center, Germany. Professor Erich Schumann adjusted his goggles against the Baltic wind. His gloved hand hovered over a chrome lever. The 47-year-old physicist's breath fogged in the cold air. Behind him, a team of engineers tensed. The 50-foot steel parabola before them hummed with building energy. Its focal point glowed faintly blue. Schumann's thumb pressed down. A thin, invisible beam lands toward a target 500 yards away. A wooden shed erupted in splinters. Flames licked the charred remains. The engineers cheered. Schumann's face stayed grim. He knew this was just the beginning. The death ray, Hitler's dream weapon, was no longer a fantasy. It was becoming a terrifying reality. The origins of the Nazi death ray project trace back to 1935. Adolf Hitler had grown obsessed with superweapons. He wanted a tool that could turn the tide of any war, a weapon that would strike fear into the hearts of enemies. German military leaders scoured the country for scientists who could make this vision real. Erich Schumann was their man. A graduate of the University of Berlin, he had made a name for himself in nuclear physics, but his true passion lay in directed energy. He believed concentrated electromagnetic waves could destroy targets from miles away. No bullets, no bombs, just pure invisible force. Schumann's early experiments were crude. He used modified radio transmitters to generate low-power beams. The results were underwhelming. A few melted light bulbs, some disrupted radio signals. Nothing that could harm a tank or a plane, but he refused to quit. He argued that with enough funding and resources, the technology could be scaled up. The Nazi high command was skeptical at first. They preferred to pour money into tanks and warplanes. But as the war dragged on and losses mounted, their tune changed. By 1939, Schumann had his laboratory, a sprawling complex at Piedmont, the same site where V-2 rockets were being developed. The team's first breakthrough came in 1940. They discovered that microwave radiation, when focused into a tight beam, could heat materials to explosive temperatures. The key was a device called a cavity magnetron. Developed by British scientists a year before, it could generate intense microwave energy. The Nazis obtained a copy through a spy network. Schumann's engineers reverse-engineered it. They built a larger, more powerful version. It weighed over a ton. It required a generator the size of a small truck. But it worked. In tests, it melted a steel plate in 10 seconds. It ignited gasoline from 300 yards away. Schumann named the project Die Glock, the bell, not for its shape, but for the deep, resonant hum it emitted when active. The name stuck. By 1941, the team had built a prototype. It stood 12 feet tall. Its parabolic dish was made of polished aluminum. It was mounted on a track chassis, borrowed from a Panzer tank. This allowed it to be moved into different positions. The generator ran on diesel fuel. It consumed 50 gallons per hour, but the power output was staggering. 1.2 megawatts of microwave energy, focused into a beam less than a foot wide. The first field test was held in June 1941, a remote training ground in East Prussia. The target was an old French tank. The bell was positioned 800 yards away. The crew activated the generator. The dish rotated toward the tank. A high-pitched whine filled the air. Then silence. The beam struck the tank's armor. At first, nothing happened. Then smoke began to seep from the engine compartment. A minute later, the tank erupted in flames. The armor had not been penetrated. but the heat had ignited the fuel and lubricants inside. The team cheered. Schumann took notes. He calculated that the beam could disable a tank from over a mile away. It could bring down a plane if aimed at its engines. Word of the success reached Hitler. He demanded a demonstration. In September 1941, Schumann and his team set up the Bell at a military base outside Berlin. Senior officers and Nazi officials attended. The target was a captured British Spitfire. The Bell was fired. The plane's fuselage glowed red-hot. The wings buckled. The engine exploded. Hitler was ecstatic. He ordered 100 units to be built. He wanted them deployed along the Eastern Front to stop the advancing Soviet tanks, to turn the tide of the war. But there were problems. The Bell was not ready for mass production. The magnetron was prone to overheating. It failed after 15 minutes of continuous use. The generator was too bulky. It could not be moved quickly. It required a crew of 10 to operate, and the beam was difficult to aim. It scattered in bad weather. It could be deflected by metal surfaces. Schumann's team worked around the clock to fix these issues. They developed a liquid-cooled magnetron. It could run for an hour before needing maintenance. They simplified the generator, reduced its weight by half. They added a radar guidance system, borrowed from night fighter squadrons. It could track moving targets and adjust the beam automatically. By early 1942, the improved prototype was ready. It was smaller, more reliable. It could be operated by a crew of 5. It had a range of 1.5 miles. The beam could be adjusted from a narrow focus for armor penetration to a wider spread for anti-aircraft use. The team conducted more tests. They destroyed 12 tanks, shot down 3 dummy planes, disabled a convoy of trucks. The results were promising, but production was slow. Germany's industrial capacity was stretched thin. Steel and copper were needed for other weapons. The Bell's components required precision manufacturing, something that was becoming harder to achieve as Allied bombing raids intensified. The first operational unit was deployed in July 1942 to the Eastern Front near Stalingrad. It was attached to a panzer division. The crew was trained for weeks. They set up positions outside the city. Their orders were to target Soviet tank columns. On the morning of July 17th, they got their chance. A battalion of T-34 tanks approached. The Bell was activated. The radar locked onto the lead tank. The beam struck. The tank's engine caught fire within seconds. The crew bailed out. The next tank was hit. It exploded. The Soviet advance stalled. The Bell crew fired repeatedly. They destroyed 7 tanks in 20 minutes. The rest of the column retreated. The success was short-lived. Later that day, Allied bombers attacked the position. The Bell's generator was hit. It exploded. The crew suffered heavy casualties. The unit was put out of action. Schumann was devastated. He argued for better protection, for underground bunkers to house the generators. But resources were scarce. The High Command prioritized other weapons. The Bell project was put on the back burner. But Schumann refused to give up. He shifted his focus. He began working on a smaller, portable version, something that could be carried by infantry, a death ray rifle. The concept was simple, a handheld device that emitted a low-power microwave beam. It would not destroy targets, but it would disable them. It could heat the ignition systems of vehicles. It could disrupt the electronics of aircraft. It could even cause temporary blindness in enemy troops. The prototype was built in 1943. It weighed 30 pounds. It had a battery pack that lasted for 10 minutes of use. The beam was focused through a small parabolic dish. In tests, it disabled a Jeep from 50 yards away. It caused a soldier to collapse in pain when aimed at his eyes, but it had limitations. The range was short. The battery life was too brief. It was fragile, easily damaged in combat. The military deemed it impractical. The project was abandoned. Schumann's attention returned to the original Bell. By 1943, the war was turning against Germany. Allied forces were advancing on all fronts. The need for a superweapon was more urgent than ever. Hitler ordered the Pigeon team to accelerate production. They were to build 50 units by the end of the year. But the factory was hit by Allied bombers in August 1943. The main assembly line was destroyed. Key components were lost. The team was forced to relocate to a smaller facility in the Harz Mountains. The new location was a former mine. It offered protection from bombing raids, but the conditions were harsh. The team worked in damp, cramped tunnels. Supplies were scarce. Food and fuel were rationed, but they pressed on. By early 1944, they had built 12 Bells. They were deployed along the Western Front to defend against the expected Allied invasion. The first combat use against aircraft came in June 1944. D-Day. Allied planes filled the skies over Normandy. A Bell unit near targeted a formation of American C-47 transport planes. The beam struck one plane's left engine. It caught fire. The plane crashed into the English Channel. Another plane was hit. Its hydraulic system failed. It crashed into a field. The Bell crew claimed 2 kills, but they were soon overwhelmed. Allied fighters strafed the position. The Bell was damaged. The crew was forced to abandon it. By this point, the project was in trouble. The team was running out of materials. The magnetrons were failing at an alarming rate. The generators were breaking down. Schumann was also facing pressure from the SS. They suspected him of sabotage, of deliberately slowing the project. He was questioned twice. His laboratory was searched. He managed to avoid arrest, but his position was precarious. The final breakthrough came in March 1945. The team discovered that by combining microwave radiation with ultraviolet light, they could create a more destructive beam. The ultraviolet light ionized the air in the beam's path. This allowed the microwave energy to travel further. It increased the beam's penetration power. In tests, it melted a 2-inch steel plate in 5 seconds. It disabled AV-2 rocket in mid-flight. Schumann believed this new version could turn the tide. He called it the Todestral, the death ray, but time was running out. Allied forces were closing in on the Harz Mountains. The facility was surrounded. On April 12, 1945, Schumann ordered the team to destroy all prototypes, all plans, all research notes. They loaded the equipment onto trucks. They drove to a nearby lake. They dumped the bells and generators into the water. They burned the documents. Schumann took a small notebook. He hid it in his coat. He hoped to continue his work after the war. 2 days later, American troops captured the facility. They found nothing but charred remains and empty tunnels. Schumann was taken prisoner. He was interrogated by Allied intelligence. He refused to talk about the death ray. He claimed the project had been a failure, that it never progressed beyond early prototypes. The Allies had their doubts. They searched the lake. They recovered parts of a bell. They sent them to laboratories in the United States. The post-war analysis was revealing. The captured components showed advanced engineering. The magnetron was more powerful than anything the Allies had at the time. The parabolic dish was precision-made. The radar guidance system was state-of-the-art. Scientists concluded that the Nazi death ray had been nearly operational. It could have been a game-changer if deployed earlier, if production had not been hampered by bombing raids and material shortages. Schumann was never charged with war crimes. He was released in 1947. He moved to Argentina. He worked as a consultant for a private company. He never resumed his death ray research. The notebook he had hidden was never found. It is believed to have been lost or destroyed. The legacy of the death ray lives on. After the war, the United States and Soviet Union both launched their own directed energy weapons programs. They built on the work done at Piedmont. The first American microwave weapon was tested in the 1950s. It was used to disable enemy electronics. The Soviets developed a similar system. Today, directed energy weapons are standard in modern militaries. They're used for missile defense, for disabling drones, for riot control. The Nazi death ray project was a product of desperation, a last-ditch attempt to win a war that was already lost. It was built with stolen technology, with forced labor, with resources diverted from other, more practical weapons. But it was also a testament to human ingenuity, to the power of science when pushed to its limits. Erich Schumann died in 1985. He never spoke publicly about the death ray. His family claimed he had regretted his work for the Nazis, that he had been haunted by the potential destruction his weapon could have caused. But there is no way to know for sure. His notebooks are gone. His colleagues are dead. The truth about the death ray may never be fully known. What we do know is this: the Nazi scientists came closer than anyone realizes. They built a weapon that could have changed the course of history. A weapon that was both brilliant and terrifying. A weapon that remains a cautionary tale about the dangers of using science for destruction, about the consequences of letting fear and desperation drive innovation. Today, the lake where the bells were dumped is a popular tourist spot. Divers occasionally find fragments of the equipment, rusty pieces of metal that once held the power of a death ray. They are reminders of a time when the world stood on the brink, when a single weapon could have rewritten the pages of history, when the line between science and madness was dangerously thin. The story of the Nazi death ray is not just about a failed weapon. It is about the choices we make, about the responsibility that comes with knowledge, about the need to use science for good, not for evil. It is a story that continues to resonate, a story that warns us to never forget the lessons of the past, because the technology that can save us can also destroy us. And the line between the two is often just a single decision away. As we look to the future, as we develop new technologies, as we push the boundaries of what is possible, we must remember the Nazi death ray. We must remember Erich Schumann and his team. We must remember the potential for destruction that lies within every invention. And we must choose wisely, because the choices we make today will shape the world of tomorrow, for better or for worse. The death ray may have been a failure, but the lesson it teaches is timeless, and it is up to us to learn it before it is too late.